Vectors are a very important concept in physics, and so we really need to discuss those before we can go on to too many principles. So a vector quantity and a scalar quantity are two different concepts. So let's begin by talking about scalar quantities. A scalar quantity is a parameter in physics that only has size. Examples of scalar quantities might include mass, temperature, or speed. These are quantities that only have a size or a magnitude. A vector quantity also has a size or a magnitude, but in addition to that, it will have a direction. So we really want to get an understanding of what vectors are all about. Some examples of vector quantities include position, velocity, and momentum. So let's consider velocity as maybe the easiest vector to begin to understand. Now you'll notice that I say here that speed is a scalar quantity. And that's a true statement. So I might be driving down the street at 30 miles an hour, and that would be my speed. But if I were to say I was driving down the speed at 30 miles per hour and I was going south, I've added a direction to that. And so now that's a vector quantity as opposed to a scalar quantity. If you're driving down the street at 30 miles per hour, you and I have the same speed. But if I'm going south and you're going east, we have different vector velocities, and that's going to be very important as we move on in physics. Vectors can be added in a number of different ways. The first of these that we'll talk about is geometric addition, and basically what this is a graphical version of adding vectors. In other words, we're going to draw vectors and we're going to add them using the drawings. Addition of vectors follows the commutative principle and the associative principle. And as we work with these vectors that we've added together, we're going to want to really take advantage of the law of cosines and the law of sines that we learned back in trigonometry. If I'm drawing these vectors on a piece of paper, I'm going to want to use a ruler and a protractor, because drawing vectors involves giving them a size or a magnitude and a direction. So I'm going to need a ruler to give them the proper length, and I'm going to need a protractor to give them the proper direction. A good example of adding vectors together geometrically or graphically is orienteering on a map. So here's a map of Casper. We're going to assume this map has north pointing to the top of the map. And let's make my starting point right here at this position. And what I'm going to do is I'm going to move to a new position one block to the north. So that new position is position A. I've traveled one block to the north. And then I might turn to the right and travel one block to the east. So my second travel was B, one block to the east. So my new position, compared to where I started, is about 1.4 blocks north and east. And that might be vector C. And so having done that, I can say that A plus B is equal to C. Now you might imagine that I might have traveled one block to the east first. And so this is going to be the same B. I'm traveling one block to the east. It doesn't matter where my vector starts. This vector B and this vector B are the same vector. They're both a vector that has a magnitude of one block and points to the east. So they're the same thing. And then I'll travel one block to the north, and that's vector A, the very same vector A that I had over here, has a magnitude of one block and a direction of north. And you can see when I do that, I end up in the same place that I did when I went A then B. So B plus A is also equal to C. And so that's the commutative property. B plus A is equal to C. So A plus B is equal to B plus A. So a vector addition obeys the commutative property. Now in a similar fashion, I might travel one block to the north, one block to the east. So there's A, there's B, and then perhaps one block to the south. Call that C. So I did A plus B first, and then I did C. And so that would be A plus B, did that first, and then I add C, and I'm going to end up at some location, we'll call that D. So there's D. So imagine, if you will, I walked one block to the north, one block to the east, one block to the north, one block to the east, took a break, and then I want one block to the south. I'm going to end up at D. Well, what if I went one block to the north, Then I took my break, and then I go one block to the east and one block to the south. I still end up at D, but the B and the C kind of came together because I took a break after A. So that I might write as A plus parentheses B plus C, and I still ended up at D. So vector addition has obeyed the associative property as well. That is to say, A plus B in parentheses add vector C is the same as A plus parentheses B plus C. Those are going to give me the same value, that value being D. Now vectors don't have to be north, south, east, or west, so I might have gone A, still to the north, but perhaps B is a little bit to the northeast. So there's B. Then my final vector is C, and that would be A plus B. So you're adding them together. A plus B is equal to C. Notice the arrangement here. I start off at the origin. The tail of vector A travels away from the origin and points in the direction of travel. And then the tail of vector B starts at the tip of vector A, and it travels in the direction of B. The final sum of the two vectors starts with its tail at the origin A, the tail of A, but it ends at the tip of B. So I started at the tail of A, and I ended at the tip of B. That's sometimes called the tip-to-tail technique for adding vectors. All right, so let's look at another one. In this case, let's travel like we might if we were a bird. And so I'm going to start at the origin. I'm going to fly to the northeast, and there's vector A. I'm going to fly to the southeast. There's vector B. And then I'm going to fly to the southwest. And there's vector C. My final position with respect to this origin is this vector D here. And again, I start at the origin with the tail of A. I move in the direction of A, and then there's my tip. Then from B, I start at the tip of A. I draw my vector B in the direction it's traveling for the length it's traveling. And then C starts at the tip of B, and it travels in its direction. This is the length that it travels. And then the sum of those three vectors starts at the tail of A and ends up at the tip of the last vector, in this case, C. And so D is in this direction to the southeast a little bit and has that length. Right? And I could do 4, 5, 6, any number of vectors more if I so desired. That's how you do vector addition in a graphical way. And we'll look at other methods of addition later on. Okay, sometimes it's easy for us to break vectors down into components. Components that would point in the x direction, components that would point in the y direction. So let's take a look at this. Here's our same map. We're going to put the origin in the same location. I'm going to draw the y-axis to the north. So there's the y-axis, and I'm going to draw the x-axis to the east. So there's the x-axis. And now let's put in a vector. So here's a vector, and I'll call it A again. So A is going to have a direction to the north and to the east. In this case, more north than east. And it also has a magnitude. Now the size of this line that I've drawn, this vector that I've drawn, that's the magnitude of that vector. And when I talk about the magnitude of the vector, in this case A, there's A. The magnitude of the vector is kind of like its size or the absolute value. And so I'm going to write the magnitude of the vector that way. I also might write it this way. That's just the letter A, but there's no vector sign over the top. So I'm interested in how long A is. And so what I do is I say, well, A has a piece that only goes to the right or to the east. And that might be right here. And then there's another piece that only goes to the north, and that might be right there. And so I'm going to call this the x component of A, and I'm going to call this the y component of A. The x component is the piece of A that points in the x direction. The y component is the piece of A that only points in the y direction. Now, since these point in the x and the y direction, they must be at 90 degrees to each other. And so this yellow triangle that I've drawn is a right triangle. And so I can say that a sub x squared plus a sub y squared is equal to a squared. Or I can say a is equal to a sub x squared plus a sub y squared, all under the radical. I'm just using the Pythagorean theorem there to discuss the size of A. I would also say that there's an angle here. We'll call that angle theta. That's the Greek letter theta. In case you're not familiar with it, that's the Greek letter theta. And theta will always be measured from the positive x-axis. That's by convention, so that there's no ambiguity. We always measure it from the positive x-axis. And a positive angle theta will always be measured in the counterclockwise direction. So this is a positive direction when it comes to the angle theta. So if we examine this triangle, we can see that theta is this inside angle, and the tangent of theta is opposite over adjacent. Got to go back to your trigonometry on triangles. And so we can say the tangent of theta then is a sub y over a sub x. All right, so the tangent of theta equals a sub y over a sub x. Or theta is equal to the arctangent of a sub y over a sub x. And that angle would be measured either in degrees or radians, depending upon what you want to use. Let me remind you from previous lectures, that is a dimensionless quantity. Now, what if I'm in a different quadrant? What if B is off in this direction? There's my vector B. Now, in this scenario, my angle theta is here. But this is what we refer to, I'll call that alpha, as the reference angle for A. So notice B in the x direction, the x component of B points to the left. The y component of B still points up. Now this is important because the x component of B pointing to the left means that it's negative. So B sub x is less than 0. Well, let's pretend then that theta has a value of 150 degrees. Then alpha must have a value of 30 degrees. And so if I take the sine of alpha, the sine of alpha is equal to the sine of 30 degrees, and that's equal to 1/2. You pop that onto your calculator. The sine of theta equals the sine of 150 degrees, and you're going to find out that's also equal to 1/2. But if you look at the cosine of alpha, you're going to get radical 3 over 2. Now remember, cosine is adjacent, and adjacent to alpha was b sub x. This was alpha in here. So the cosine of 30 degrees is radical 3 over 2. But remember that to be precise, we really want the cosine of 150 degrees. And if you put that into your calculator, you're going to get minus radical 3 over 2. But that makes sense because remember that the cosine is adjacent, which is b sub x, over hypotenuse, which is b. But b sub x is in fact negative. It's pointing to the left. So in this quadrant, my sine is positive, but my cosine is negative. And that's going to make sense because the x component, which is associated with the cosine, is negative. Now we'll find in the third quadrant here, the tangent is going to be positive, but the sine and cosine are negative. And that makes sense because both the x component and the y component are negative. So the sine, which is going to be associated with the y component, because that's opposite the angle, the sine is going to be negative because the y component is negative. Remember, the hypotenuse will always be positive. The cosine will be negative because the x component also points in the negative direction. Y component's pointing down, x component's pointing left. But the combination of the two, the tangent, which is opposite y component over adjacent x component, both negative, will be positive. And then in this quadrant, we're going to find the y component is negative, so the y component is less than 0. That's associated with the sine, so the sine is less than 0 here, but the cosine is associated with the x component. The cosine will be greater than 0. So for these 4 quadrants, in this first quadrant, all the trig functions are going to be greater than 0. In this one, only the sine function is greater than 0. In this one, only the tangent function is greater than 0. And in this one, only the cosine function is greater than 0. We've come up with a little phrase to help us remember that, and that is that all students talk crazy. All functions are positive, sine is positive, tangent is positive, cosine is positive. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4 in the Cartesian plane. Now you want to be really careful about this because if you're working with your calculator, you might not get the proper signs, especially down here in the third quadrant. And if you're working with tangent, it's really going to become confusing because the tangent is positive here in the first quadrant and in the third quadrant. So be very careful about what you let your calculator tell you. Now there's another coordinate system that we will sometimes use, and I find this easier to use on my calculator than the Cartesian system. Okay, this is the Cartesian system, or the rectangular system. It uses the x and y system. We'll talk more about this later. But the polar system can be much easier, and the polar system really works pretty straightforward. We're going to work with the magnitude of the vector, which I've called r in this case, and the angle theta. And so if I have a vector quantity A, it might have a magnitude, say, of 1.5 blocks. I always want to keep my units in mind. So it has a magnitude of 1.5 blocks, and maybe it's at an angle of 53 degrees. So the way I'll write this, I'll put an angle sign here like that, and I'll write 53 degrees. So this would be the polar form of the vector A, 1.5 blocks at an angle of 53 degrees. And you want to figure out on your calculator, how do you make it display vector quantities in polar form? It's going to be very handy when you do. In physics and engineering, there are other coordinate systems that we're going to work with. We'll pretty much stick with the rectangular and the polar system. If you take more courses in calculus or in engineering, you'll learn about these others. The cylindrical system and the radial transverse system are pretty much the same, and they're very much related to the polar system. We're going to look at the polar system both in its cylindrical format and its spherical format. And we'll get to that later on. There's also a normal tangential system, and you'll come across that again in the third semester of calculus or in an engineering class later on. But we're going to stick right now to just the rectangular and the polar system, and we're pretty much going to stick with 2 dimensions for a while. So we want to talk about components of vectors because they're going to really make a difference for us. And we've already talked about this a little bit, so let me redraw an x and y coordinate system. So here's x and here's y. And let me have a vector quantity A, and we already know that A has a component in the x direction and a component in the y direction. So I'm going to label that a sub x and a sub y, and let me just say that those are also vectors. They have a magnitude and they have a direction. So keep in mind, if I travel to the east and then travel to the north along a sub x and a sub y, my final location I could have gotten to by simply starting at the origin and traveling in a straight line to reach that final destination here. And so we can say that A is equal to a sub x plus a sub y. But it would be nice if I could talk about a sub x as a directional vector and a sub y as a directional vector and put them together and get my final A. And that's exactly what we're going to do. So I need to define what are referred to as unit vectors. And unit vectors can be displayed in a number of different ways. Almost always they'll have a little caret symbol over the top, and that will indicate a unit vector. So the unit vector in the x direction is going to point to the right, and I'm going to label that unit vector I hat. And the unit vector in the y direction, I'm going to label that j hat. Now because they're unit vectors, that means they have a size or a magnitude of 1. Not 1 foot, not 1 inch, just 1. Okay, there's no units attached to the unit vector. Bad use of terms, but it's the way it is. So think of the unit circle you learned about in trigonometry. It's the same idea here. And so a sub x has a size and a direction. So this vector a sub x can be written as some size, a sub x, that's just the magnitude, times the unit vector in the x direction. So a sub x can be written as a size a sub x times unit vector I. And a sub y can be written as a sub y, some magnitude, times the unit vector in the y direction, and that's j hat. And so my final vector A, which is the sum of a sub x and a sub y, can be written as a sub x in the I hat direction plus a sub y in the j hat direction. Now in this class we're going to stick pretty much with I hat and j hat in the x and the y direction. And when we get into 3 dimensions, we'll see there's a k hat to symbolize the z direction. but we won't get to that for a little bit. Some books will write e sub x with a hat, e sub y with a little hat. That would be the unit vectors in the x and the y direction. You might also see e sub I hat and e sub j hat. So just some other unit vectors you might have come across in other textbooks or other classes. It depends upon the teacher and where the teacher learned. Different parts of the country will use different unit vector notation, and other countries will use different unit vector notation. So let's assume for a minute that A is a vector, and the magnitude of that vector is 10, and the angle with respect to the positive x-axis is 30 degrees. Then I can write, so if I draw this out with a triangle, this has a size of 10, and this is the angle of 30 degrees, this must be 5, and this is 5 times the square root of 3. And so a sub x is 5 square roots of 3 in the I direction, and a sub y is 5 in the j direction. Now if I had another vector, and maybe that vector is b, and perhaps b has a size of 14, and it's at an angle of 135 degrees. So if I draw my axes, here's A, that's at an angle of 30 degrees. And now let's start with B. I'm going to start over here, and I'm moving off in this direction. This one has a size of 10. This angle here is 135 degrees, and this has a size of 14. Then this can be written as 14 cosine of 135 degrees, because that's the x component moving along in this direction, cosine of 135 degrees in the I hat direction, plus 14 times the sine of 135 degrees in the j hat direction. Now notice the cosine of 135, if you work that out, you're going to get radical 2 over 2, but it's going to be negative. So this is equal to negative 14 radical 2 over 2 in the I hat direction, plus 14 radical 2 over 2, because the sine of 135 is positive, the sine is positive in the second quadrant, cosine is negative in the second quadrant, in the j hat direction. And so I'm going to get minus 7 radical 2 in the I hat direction, plus 7 radical 2 in the j hat direction. And so if I add these together, there's C. I could have gotten C by taking this vector plus this vector plus this vector plus that vector. That's going to be, there's the first one, a sub x. Here's a sub y right here. Here is b sub x. And here is b sub y. And remember, if I go tip to tail, I end up in that direction. And so a plus b is going to be 5 radical 3 in the I direction, plus 5 in the j, plus negative 7 radical 2 in the I direction, plus 7 radical 2 in the j direction. And so that will end up being, the I hats will go together, 5 radical 3 minus 7 radical 2 in the I direction, plus 5 plus 7 radical 2 in the j direction. In other words, you put all the I components together, you put all the j components together. And if you work this out mathematically, you're going to get a number with a little bit of x in the negative direction and a pretty good sized y. And that's exactly what you see when I draw it out. It's not exactly to scale, but it's pretty close.